In this video, we will be looking at the distillation of crude oil. One of the most important processes at an oil refinery is distillation. Distillation is the first step of turning crude oil into usable products. The process starts with boiling. When you heat water, it will reach 212 degrees Fahrenheit. This is the boiling point. The water will not get any hotter than this. At this point, the heat changes the water into steam. Turning liquid into vapor. When the steam drops below the boiling point, it turns back into water. You can see it condensing on the lid. All liquids have their own boiling point. The size and shape of the molecules determine the boiling point. The larger the molecules, the higher the boiling point. The smaller the molecules, the lower the boiling point. Here we have two different liquids. One liquid is made up of small molecules, and the other is made up of large molecules. If we mix the two together, we can separate them after they are mixed. One way of doing this is by distillation. If we heat the liquids inside the tube until they are vaporized, then feed the mixed vapors to a column where they are cooled. Near the bottom of the column, the vapors are cooled to just below the boiling point of the heavy liquid. It will condense here and can be drawn off. But it's too hot for the light liquid to condense, so it rises further up the column where it is cooled sufficiently to condense. At the top of the column, the light liquid collects, and at the bottom of the column, the heavy liquid collects. The light liquid will contain a small amount of the heavy, and vice versa. But these amounts are small because the boiling points are far apart. Here we have an example of a fractionating column that is used for instructional purposes. It has a heater or boiler on the bottom that is used to heat a mixture of water and ethanol. As we move up the column, we can see the different trays. Most of them are a sieve type tray, but the second one up is a bubble cap tray. After the heater is turned on, we can see the vapors condensing on the first tray as the liquid begins to heat. After a while, as more of the liquid is evaporated, we can see it start to condense on the other trays. Once the process has been running a while, enough liquid condenses on the bubble cap tray so we can see how the bubble caps function in the process. The holes in the sieve type trays allow the vapor to pass through, and the pressure of the vapor passing through the tray keeps the liquid on the tray. But as we lower the temperature of the boiler, there is not enough vapor passing through the holes on the tray, so the liquid will start weeping back down through the holes on the tray. This shows us how the vapors and liquids react in a fractionating column. Crude oil is a mixture of many types of molecules called hydrocarbons. There are thousands of them, and their boiling points are so close together it would be nearly impossible to separate them individually, but this is not necessary. Instead, crude oil is lumped into groups called boiling fractions. Each one covering a range of boiling points. Think of crude oil as a bunch of shuffled up playing cards. The gasoline is the 4s, The turbine fuel is the 6s. The diesel fuel is the 8s. And the fractions with the highest boiling ranges are the kings and queens. The separation takes place in fractionating columns. To separate all of them requires 2 stages: crude distillation and vacuum distillation. Crude oil is pumped from storage tanks to a furnace where it is heated, but it is only heated enough to vaporize some of it. When it gets to the column, it is a mixture of vapors and liquids. Once inside, they separate. The liquids fall to the bottom. They are the queens and kings. They will be dealt with later. The vapors, the 4s, 6s, and 8s, will rise. As they pass through the tray, they are cooled. When their temperature falls below the boiling point of the heaviest fraction, this fraction will condense on the tray and be drawn off. The rest of the vapors will rise up through this tray to the next, where they cool further, below the boiling range of the next heaviest fraction. This condenses, and it too is drawn off. The vapor that is left is drawn off the top of the column and is condensed. There are several ways of separating fractions. One way is to use bubble cap trays. On each tray inside the column are mushroom-shaped fittings called bubble caps. The hot vapors rise up through the stem, then back down underneath the bubble cap, making contact with the liquid on the tray. If liquid and vapor are of the same fraction, the liquid will be cool enough to condense the vapor. So if the liquid consists of 8s, the vapor that condenses will also be 8s. But if the vapor is of a lighter or lower boiling fraction, it will find this liquid too hot to condense in. It will bubble through and rise to the next tray still as vapor. If the liquid consists of 8s, these bubbles will be 6s and 4s. In practice, however, the vapors are so closely intermingled they never separate completely the first time. Some of the vapor that belongs on this tray is carried through to the lighter vapors and to the tray above. Here it condenses, but now it's on the wrong tray. To return it to where it belongs, a steady stream of liquid is overflowed to the tray below. Since this tray is hotter, the 6s that come down are re-vaporized and again rise to the next tray. But it is the right temperature for the 8s, and this time they stay condensed. This type of mixing and separating goes on all the time until all the fractions are sorted out, liquids falling and vapors rising all the way to the top. At the top of the column where it is coolest, and only the lightest fraction is left, the 4s, this vapor is condensed but still contains stray 6s. So here too a steady stream is returned to the tray below. The 6s remain in the tray and the lighter 4s are re-vaporized. Only 2 trays have been shown here, each tray separating one fraction. But in practice, several trays are needed to separate each fraction efficiently. An actual crude distillation column may contain more than 50 trays. The top fraction goes to make gasoline, the next one down, turbine fuel, the next diesel fuel and home heating oil. The liquid settles to the bottom as residue, but it still contains other useful products. The fractions in the residue boil at very high temperatures, some more than 1,000 degrees. At these temperatures, the molecules will crack apart before the fractions boil. To prevent this, they must be made to boil at lower temperatures by vacuum distillation. When a liquid is heated, the pressure of its vapor increases. This pressure pushes against the pressure of the atmosphere. When the vapor pressure is high enough to overcome the atmospheric pressure, the liquid boils. But the atmospheric pressure on the liquid can be reduced by pumping out some of the air and creating a partial vacuum in the flask. Here, the pressure has been reduced enough to make the liquid boil at room temperature. Similarly, if the pressure inside the distillation column is reduced, the heavy fractions can be boiled at lower temperatures so they can be distilled without their molecules cracking apart. From the vapor entering the vacuum distillation unit come more products. The lighter fractions go to the cat cracker. From the next fraction come wax and lubricating oil. The heaviest fraction remains a liquid and is withdrawn into processing for industrial fuel oil and asphalt. For one thing, the gasoline that is distilled directly from crude oil, called straight-run gasoline, by itself is not high enough octane for the modern vehicle. When enough gasoline, turbine fuel, and diesel fuel have been distilled, a lot of heavy fuel oil is produced as well. By using another process, cracking, heavy oil can be converted into high-octane gasoline. Heavy oil is made up of molecules that can be represented like this. When heated to very high temperatures, their movements become violent. Eventually, they shake apart or crack. In cracking into smaller molecules, most of them change their shapes and take on new properties. Most important of these properties is a higher octane gasoline. This reshaping process depends on a substance called a catalyst. The catalyst is any substance that stimulates a chemical reaction without itself being affected by it. Hundreds of substances do this, some more complex, some more simple, like these pieces of copper. This demonstration shows how they work. These two liquids normally react very slowly when they are mixed together. Now we add the copper. The reaction is speeded up. When the action is complete, the catalyst is unchanged and can be used again. Many catalysts are used in a refinery. One of the most important uses is in a catalytic cracking unit, a cat cracker. The catalyst used here consists of silica and alumina in the form of a fine powder. To do its job effectively, each grain must present the largest area possible to the heavy oil that is to be cracked. The catalyst also has to circulate freely in the cat cracker, and to do this, it must be made to behave like a liquid. At rest, the powder is a solid mass and will support a metal object. But if gas or vapor is blown through, it is turned up or fluidized. Now the object will sink as if it was in a liquid. To do its work in the cat cracker, the catalyst must be heated to more than 1,000 degrees Fahrenheit. Then, at the base of the unit, hot catalyst and heavy oil meet, and the cracking begins. The heavy oil is immediately vaporized, and the vapor in turn fluidizes the catalyst. This mixture rises to the reactor. Here, the heat and the catalyst complete the cracking reaction. Before long, however, carbon forms on the catalyst, clogging the openings. This reduces the working area and makes the catalyst less effective, so it has to be cleaned. It's fed to a regenerator where the carbon is burned off. The burning also heats the catalyst back to its working temperature, and it's ready for use again. This is the cycle of the cat cracker. Steady flow of catalyst meets a steady flow of heavy oil, and cracking goes on continuously, producing new shapes of high-octane gasoline. Besides gasoline, cracking produces petroleum gases and diesel fuel. All these products are passed to a distillation column where they are separated. But cracking doesn't provide enough high-octane gasoline to meet the demand. So low-octane straight-run gasoline is converted to high-octane gasoline by catalytic reforming. Straight-run gasoline consists mainly of short, straight molecules. To upgrade these shapes, these molecules must be changed, that is, reformed. As before, heat and a catalyst are required. And again, high-octane gasoline is produced. The catalytic reformer uses platinum as a catalyst. A thin film of platinum is coated on pellets of aluminum oxide, and they are packed in the reactors. But reforming requires a lot of heat, and the process has to be done in 3 or more stages. The straight-run gasoline is heated to more than 900 degrees and fed into the first reactor as vapor. As it passes through the catalyst, reforming begins. But so much heat is absorbed by the reaction that it stops before reforming is complete. When it leaves the first reactor, the vapor is only partially reformed, so it must be reheated and sent to the second reactor. Again, the vapor cools below its proper reaction temperature, and the reaction stops. To reform the vapor completely, it must be reheated once more and fed to the third reactor. Here, any remaining straight-run gas molecules change into high-octane gasoline. During most of these reactions, a lot of hydrogen is released. Its presence not only inhibits the formation of carbon on the catalyst, it is also valuable for use elsewhere in the refinery. These then are the principal refining processes: crude distillation and vacuum distillation, which separate crude oil into various products; cracking, which converts heavy oil into high-octane gasoline; and reforming, which converts straight-run gasoline into high-octane gasoline. This is only part of the story. Other processes turn out additional products, as well as providing many raw materials for the chemical industry. All in all, there are thousands of products based on petroleum, and more uses are being developed all the time.